So here we go with section 2.3, day 2, another day on continuity or discontinuity, whichever way you want to look at it. Some people look at their lives full of discontinuities and others look at it with continuities. It's kind of like glass half empty and half full. Okay, so we're going to talk about removing a discontinuity, which means taking a discontinuous function and making it continuous. And then we're going to talk about composite functions and the intermediate value theorem. The first thing we're going to talk about is all of these functions are continuous every place that they exist. All right, so if you have a function like an inverse function, it's continuous everywhere except for the place it doesn't exist, which is x equals 0. All right, polynomial functions are continuous everywhere. Rational functions are, those are actually functions divided by functions. So if you have x minus 5 and over x minus 5 times x plus 3, that's a function over a function. It is continuous everywhere except at 5, where there's a hole, and where there's an asymptote, x equals -3. The absolute value function is continuous everywhere. Sine and cosine are continuous anywhere. Our friend tangent is continuous in between its asymptotes. So between -π/2, +π/2, and at those spots there's an infinite discontinuity. Log functions are continuous when x are continuous everywhere except x, it's continuous x greater than 0. And 3 to the x is an exponential function. It's good everywhere. Rational functions are continuous everywhere if n is negative. If n equals a positive, then x has to be greater than 0. Okay. All right. Next, we're going to look at making a function continuous. All right, this function has a couple of holes, and we're going to make this at the point x equals 1. We're going to check it out. First thing we're going to do is factor the top, factor the bottom. Well, the bottom's easy. It's the difference between two squares. The top is the difference between two cubes. So, still have the same general, it should be a plus x plus 1. I think that's how we factor that. Looks good to me. A is x, b is 1. So these cancel out. And what we can do is actually find a value. This is going to be a hole at x equals 1. We can find a value to plug in for that hole. So let's put in 1 into our new function that we've created, which is really like the old function. And if we plug in a 1, we get 1 plus 1 plus 1 over 1 plus 1. Well, to me, that looks like a 3 over 2. That is going to be the value of our function at 1. So let's look at how we write our brand new function. Okay, we have x cubed minus 1 over x squared minus 1. And that's good everywhere except x equal to 1. And our value of our function at x equals 1 is going to be 3/2. Okay, so that's how we write the new continuous function. It's not completely continuous, but at x equals 1, it is continuous. All right, so let's look at this problem. Remove another discontinuity and make it a continuous function. So we're going to do the same thing with this function. Start out by got rid of the little dots. All right, so we are going to factor the top. I'm pretty sure there's an x minus 3 in there. If it's x minus 3, it must be x plus 5. So we cross out our x minus 3's, and we're left with x plus 5. So we can figure out what our function is going to be at 3. So take a 3, our function at 3 will be equal to 8. Aha. So now we're going to write our new function, f of x, equals the original function, and then it equals 8 when x equals 3, and up here x doesn't equal 3. And there we have the new function we have created, which is continuous at 3. Okay, we're going to do another example. This one is scary to people just because it has a little bit of fancy algebra. Okay, so we're going to remove this discontinuity. And we are going to change x minus 4 into the square root of x minus 2 and the square root of x plus 2. If you don't believe me, you can FOIL those two out. This is just what we call fancy algebra. Okay, so FOIL those out and check and see if I'm correct. All right, so then what we're going to do, let's take our denominator and see what value of x would actually give us 0 in our denominator. We add 2 to both sides, we get square root of x equals 2. We square both sides, squared, squared, we get x equals 4. All right, so really the value we want to plug in is 4 to our equation. So we get the square root of 4 plus 2, and that equals 2 plus 2, which is 4. All right, so our function when x equals 4 is going to be 4. So let's rewrite our brand new function. All right, with a little black pen here. You always take your original equation and set it up at x is not equal to 4. And here is x equals 4. We said our function would also be equal to 4. So that's our brand new function made into a continuous function at x equals 4. Now let's look at some of the properties of continuous functions. If f and g are continuous, then sums, differences, products, a constant multiplied times the function, and also the quotient are also going to be continuous. So check out those theorems on page, or not the theorems, but the properties on page 82. Composites, if two functions are composites of each other, then they are also continuous at a point C. Let's take a look at an example. What we're going to do is break this up into two functions. Notice we have a radical function with a polynomial function inside. Here's our polynomial function. We'll call it g of x. And our f of x function is equal to the square root of g of x. All right, so what we have is an f of x, an f of g of x. Okay, because this is really g of x. All right, so what this says is that what our theorem, this number 7, and our numbers don't make any difference in this book. That could be theorem 2500. But what it says is that the two functions are continuous, then the composite is continuous. So this polynomial is continuous. This radical function is continuous as long as g of x is greater than 0, right? So therefore, f of g of x is continuous. And that's what they want us to do, is break it down into two functions and say that the composite is also continuous. And that's all we have. I have a virus, and so do all my pens and pencils on my computer. Okay, that is the end of section 2.3, day 2. See you in class.